So, yeah, I will talk about modular multi-shape registration, a project that I'm working on together with Barbara Gris. Oh, how can I? This? Oh, this one. This one. Oh, okay. So. So the goal of our framework is to match shapes, for example, images or curves, in order to understand the differences between them or their evolution. In many cases, we want to preserve the local topology of the shapes in order to prevent holes or foldings in the deforming shapes. So we require the deformation to be a diffeomorphism. An efficient way of building diffeomorphic deformations is as flows of time-dependent vector fields. So for example, in this picture, we see a domain represented by a regular grid at the initial time and how it evolves with this time-dependent vector field, which is defined on the domain, on the deformed domain at each time point. And this also allows easy modeling of the evolution of the deforming shapes. So a possible application could be registering different observations which were taken at different time points. For example, these two lung images at different times during the breath cycle. This particular example presents several difficulties. First, we would like to incorporate some prior knowledge on the deformations of the shapes, so of the lungs and the organs and the surrounding tissue. And then second, as the lung moves during the breath cycle, it will slide along the surrounding tissue. So there we have a discontinuity at the lung boundaries. So only at the boundaries, the deformation will not be diffeomorphic, but we want to still preserve the local topology in each lung and in the surrounding tissue. So one way of incorporating a deformation prior into the deformations is by deformation modules, which uses a vocabulary of structured deformations built as flows of vector fields. We will use this framework and marry it with the multi-shape registration originally introduced for large deformation diffeomorphic metric mapping. Yes, so I will explain both frameworks, then explain the key steps in combining them, and show some numerical examples on synthetic data. So let us look at the example for curve registration. Here we see two curves where we want to match the black shape, which we call the source, onto the red shape, which we call the target. And looking at the curves, we could assume a uniform shrinkage in the left half and a uniform expansion in the right half of the curve. So in the first attempt, we use unstructured deformations as in the LDDMM framework, and this is how the shape evolves. So so we see that we have a perfect curve matching. However, the inside in the curve in the ambient space is somehow distorted. It doesn't represent this uniform scaling that we might assume or that we wish to model. So we can use deformation modules to incorporate this prior knowledge on the deformation. Deformation modules provide a vocabulary of structured deformations, for example, local scalings or physically motivated deformations. So for this example, we use two local scalings, which are centered at each dot in this picture, and also a large-scale translation. And then this is how the shape evolves. So here we see a comparison of the two final deformations. We have the perfect matching, but somehow distorted deformation for the unstructured deformation. And then we have a deformation created by deformation modules, which may represent the general structure of the deformation better. And it also allows to interpret the amount of scaling in each part of the shape. So deformation modules, as introduced by Barbara Gris, are defined as a quadruplet of a shape space, a space of controls, a field generator function, and a cost function. The space of controls contains the geometrical descriptor, which for the scaling is the center of the scaling. And the field generator function determines how a vector field is built given a geometrical descriptor. It is a function of the control variable h, and by choosing different values for h, we can obtain vector fields of the same structure, but different. So we build these vector fields for each time point in a time interval with varying controls over time. And then we build the finite deformation as the flow of this time-dependent vector field. And two examples are shown here for the finite deformations, where we use positive control variables for the left one to have an expansion, and negative control variables lead to a local shrinkage. Then finally, the cost function defines the cost of the deformation depending on the geometrical descriptor and the control variable. It is defined as a Sub-Riemannian metric on O on the shape space. We can, for example, choose the square norm of h for our scaling. Okay, so here I show some vector fields that are built by deformation modules. We have the negative and positive scaling, which are built by the same module, but with different geometrical descriptors and different control variables. Then we have the translation, which is a different deformation module. And we can also combine them into a compound module by adding the vector fields of each module at each time point. And then the final deformation is the flow of the sum of the vector fields. So for the study of multi-shapes, we need a way of combining deformation modules. We could try using a compound module, and this is what happens. So the compound module is a deformation module itself, and it creates diffeomorphic deformations of a certain regularity that is inherited by the deformations, by each deformation that we want to combine. So here we have quite a high regularity in the compound module because the deformations for each shape are of quite high regularity, and this prevents the shapes from moving close to each other. So we need a new way of combining diffeomorphic deformations. And the idea by Sylvain Aguillier is to associate the region and the ambient space with each shape, such that the regions don't overlap and they cover the space. So for our example of curves, we have the regions U1 and U2, which are bounded by each curve. And then we have a third region, which is the complement in the ambient space of U1 and U2. And we define a third shape, which is defined as the boundary of this background region U3. Then we compute one deformation for each of these regions or each of these subshapes, while linking them through some constraints at the boundaries. And we build the final deformation by taking each deformation in each region and putting them together like a puzzle. So this idea was formalized by Sylvain Aguillier in the multi-shape registration problem. And here we consider a multi-shape of n subshapes. So we minimize over the set of n vector fields, time-dependent vector fields. We minimize the energy functional, which consists of a regularity term and a data term, where the regularity term is the sum of the kinetic energies And the data term measures the similarity of the deformed subshape Q at time 1 and the corresponding target subshape. Then we have some constraints. We have the shape evolution and the initial condition, which are also constraints for the classical LDDMM problem without multi-shapes. And then we have this new set of constraints which model the object boundary constraints, the region boundary constraints. And this new operator CQ is a linear operator on the set of all vector fields. So we use this as an inspiration and create a new problem where we use deformation modules and multi-shapes together in one problem. So what we do is we define one deformation module for each subshape. And now we minimize over the set of all control variables instead of the vector fields. Then we replace the regularity term with the sum of all cost functions. And we have the same type of boundary constraints where now CQ acts on the set of modular vector fields. So on the set FQ of H, which are the vector fields created by each module. So to solve this problem in practice, we use a Hamiltonian approach. Solving the previous optimization problem is equivalent to solving the geodesic equations for the Hamiltonian, which is obtained by the Legendre transform of the Lagrangian energy function and the Lagrange multiplier term for the object boundary constraints. In this notation, the star stands for dual operator and the bracket notation stands for the dual pairing. So for sufficient regularity assumptions on all the functions, the set of equations has a unique solution for each initial value for Q and P. So in order to solve our optimization problem, we optimize it with respect to the initial condition for P. In order to do that, we have to compute the geodesic variables H and lambda, as shown here. And in particular, we have to invert this operator. So this operator is invertible if the operator CQ FQ is surjective. An equivalent proposition was shown by Sylvain for the multi-shape registration problem for unstructured deformations. And he pointed out that surjectivity becomes almost straightforward in a discretized setting. However, this is not the case for the modular multi-shape registration problem. So the surjectivity is in general not guaranteed, but we can easily obtain it in practice by enriching the space of vector fields, as I will explain in the two following examples. So in the practical study of multi-shapes, we can encounter two main cases where multi-shape setting is needed. The first is present in our curve example. So we have multiple shapes which are to be studied together in one ambient space. We have the regions U1 and U2 bounded by the curves, and then we have this background region U3. We would like to incorporate prior knowledge on the deformation for U1 and U2. We take, as previously, the two local scalings and the translation. And then we don't have any prior knowledge on the background deformation, so we use unstructured deformations for the background. In order to ensure consistency at the boundaries, we use what was introduced by Sylvain as identity constraints. And they force the point on the boundary of the background to move with the corresponding boundary point of the shape. So this ensures continuity. And then because of the unstructured deformation for the background, the space of vector fields is rich enough to ensure surjectivity of CQ, FQ. Using this model, this is how the shapes evolve. And yeah, you can see that by choosing the regularity of the background accordingly, we can make the shapes move very close to each other while yeah, while maintaining this structured, very regular deformation inside each shape. And you can also see how the deformation is continuous at the boundaries, but not differentiable, which is what identity constraints model. So in other cases, we could have one shape that consists of different parts which underlie quite different types of deformations. So in that case, we can view it as one multi-shape consisting of several subshapes. In this example, we want to match the two tree-shaped curves where the crown of the source has to shrink while its trunk has to expand to reach the target. So we divide it into two subshapes. One is all the region below the crown and will be deformed with the trunk. And then the other region for the second subshape is all the region above, and it's deformed with the crown of the tree. So in this case, we need another type of constraints in order to make it possible to have this expanding and this shrinking deformation right next to each other. So we use sliding constraints, which are defined by forcing the normal components of the velocities of the shared boundary points to be equal, while the tangent components can differ. In the case of shared boundaries, the surjectivity of CQ, FQs is normally not guaranteed, but we obtain it by adding small local translations to all the boundary points, the shared boundary points, not all. Yes, and we add this with a high penalty. So in this way, we can enrich the space of vector fields enough to make it surjective, while we don't change the deformation prior a lot. So this is how the trees match. Oops. And yeah, you can see this sliding between the two subshapes. So to conclude, our framework of modular multi-shape registration uses a vocabulary of structured deformations for multi-shape setting. The deformation modules allow easy interpretability of each of the deformations in each subshape, and we can enforce consistency at the boundaries according to the application. We showed the new possibilities of the model on synthetic examples, and in future work we would like to apply this also to other types of shapes, in particular images, medical images with the known segmentation and known knowledge of the deformation that comes from physical properties of the objects. Thank you for your attention.
Thank you very much for your very interesting talk. Questions?
Framework. You said that to solve your problem, you look at the geodesic equation for the Newtonian. And so you have to ensure that you're not normal at some point, right? You have to ensure that you have not normal extremas there that you couldn't get via the geodesic equations. Maybe I misunderstood the problem. Like the contrary maximum principle could have some normal extremas appearing.
I'm not entirely sure, but I think that I think this is by the assumptions that we make on the functions, like the cost functions and the data term. I think they prevent this case. Yeah. So yeah, we no, actually yes, we showed the existence of a unique minimizer. So I think this case should be avoided. Yeah.
Do you think you can extend your approach to 3D deformation?
Yes.
Okay.
Yeah.
And to groups, maybe groups equipped with I don't know, Sub-Riemannian metric like the cortex. When you see three-dimensional groups with the tangent planes, contact structures.
Potentially.
Thank you so much.
Yeah.
Okay, let's thank the speaker again.